And now to today's DDG online meeting. It gives me great pleasure to turn this event over to our discussion leader, Brian Christ from Agilent Technologies, who will introduce the panel for today's topic. Go ahead, Brian.
Great. Thank you, Sandy. And I want to welcome everyone. Good day. And today we're going to venture into a topic that we did explore about 6 years ago in one of our online meetings, but this time we're going to focus a little bit more on some degassing methods that are used in dissolution. And then to further, because of questions from an earlier discussion group meeting, maybe just talk a little bit more about the techniques for measuring, how effective was this process. So we're going to go ahead and move on to the next slide here, and start. Just to remind you that this is an ongoing session we've had with DDG for many years now. We're in about our 9th year of consecutive quarterly meetings. The website itself, the DDG, is primarily a bulletin board. It's a free online bulletin board, and this is all sponsored by Agilent and has been since its beginnings many years ago. The idea here is to really provide a communication tool for chemists, people like yourself that are dealing with dissolution, drug release methods, and so forth. We do have a mission where we do provide this forum for really scientists to talk to each other. Again, there's so many tasks that, we seem to have under control for developing, but there have been recent changes in FDA's views on maybe everything from some standard methods to issues with validation and compendial changes that are minor. But, all along some new chapters are introduced, and so this is a good forum for keeping people up to date on the things that are changing in dissolution and things that are specific to it. The site is, most of you are aware, the registration, this is just from a couple of days ago, and you see today's meeting on degassing methods. You'll also see the remaining schedule for the year and the other topics that we have coming. So please frequent this site, if not just for the bulletin board, at least to continue to register for the meeting. So as always, if you're new to this site or these meetings, welcome. And if you've been a previous attendee at these meetings or on the site, of course, welcome back. And we hope not to disappoint you at this session, since we plan to have quite a bit to discuss on deaeration, a lot of hot air on the subject, if you will. If you look back at our previous meetings, all of these are recorded. So these particular meetings, you can see a variety of topics just on, some are new topics to USP, some are proposed changes in USP chapters or FDA guidance. And we do have a considerable section on different facets of dissolution method development. But speaking of that, one big facet is the topic du jour, the deaeration, and it's important. So we'll be touching on the regulatory and compendial aspects of that as well. Joining me today is Ken Boda. Ken's a colleague of mine, and he's quite an expert on dissolution and drug release in his own right, and from his previous career before Agilent, of course, while he is with Agilent now. So Ken, welcome, and glad to have you here.
Thank you.
All right, so what are we going to talk about today? Well, if you've been to these meetings before, we throw some slides out, and hopefully the goal is to encourage thinking on your part. And as we're mentioning some things, of course, everybody has, maybe a view of how something should work, or how, the best way to do something. So we really like to hear those things. We're going to present a certain view, but that is does not always mean that this is good for everyone, but and these may conflict with some of your procedures that you do, your SOPs and so forth. But we're going to talk just openly about challenges that arise from from media that is not properly deaerated. And you'll see some clues here, because the, bubbles that form in media because when media is heated, air comes out of saturation and it forms bubbles. And these do increase turbulence, especially at a very critical part of the vessel, and that's the wall of the vessel. Very early in dissolution, these particles, as they're in a rotational motion in the vessel, are normally traveling along a very slick glass surface, if you can picture this. So there's very little shear at that interface. However, if that surface is coated with bubbles, it creates like a minefield of turbulence that as particles are going around and bumping in, all the currents that are right there at the interface are quite intense. So you can see very often a rise in dissolution results, especially from paddle methods. And incidentally, the second thing there is that bubbles on a paddle also increase its surface area, which increases agitation, which raise dissolution release rates to a point where, well, if media is not properly deaerated, it could help a product to pass, maybe that shouldn't pass. Our dissolution test is to, keep drugs from going into the market that are subperforming, those lots that are not releasing their drug at the right time. Another area with air is aggregation of particles. Air, when it's in contact with a solid particle, often will attach to it and raise it to the surface and may cause other issues with the dissolution rate, changing it from what would be a situation with no interference now could have a drastic effect on the dissolution test results. Anyway, so we look forward to your ideas as we're moving through these topics. And, just as a background, when we're talking about deaeration, we're talking about removing gases. This is primarily total gases or air from the dissolution medium. And this is primarily because gas laws is, we raise the temperature, air is less soluble as temperature rises. So this is where it degasses and forms bubbles within the media, which, as we mentioned previously, are quite an impediment to proper dissolution. So when it's heated to 37 degrees, which is the standard temperature that's used for oral drugs that are consumed, we need to understand the impact that air may have on the product. And this is not just a suggestion. This is actually a compendial requirement that you'll see in a wrap-up that, where dissolved gases are shown to interfere, they must be removed. So this is something that we need to address in method development. Just a few more notes. Why is it a concern? Well, think of how many disintegrating formulations that you have. The presence of air coating the vessel wall very often for paddles can increase the dissolution rate. Interestingly, in some different products, it may affect them in a different way. Baskets, because bubbles form in a basket and flow is restricted through a basket, may exhibit some slower results. Same thing may happen on the surface of a transdermal system that's tested with USP apparatus 5 or 6. If bubbles form on the surface of that patch, nothing is moving through right there. So it may suppress dissolution rates for some things. But mainly it's variable, and it's maybe not as position to position with the dissolution apparatus, but from test to test. Even aeration levels from purified water sources during the day in laboratories can be quite variable. And we're going to discuss the modern ways that most purified water is made and the impact that this has on dissolution. And then again, there's products that are just unaffected by dissolved gases. If they're present or not, the results are the same. So in those cases, deaeration is not required because you've proven that It is not an interference to the test. Following up with prednisone, speaking of drugs that are affected by deaeration or lack of it, this has a profound effect on release rate for the performance verification test based on the prednisone tablet. These are very sensitive to dissolved gases, and results are virtually double at early time point, which for prednisone is 30 minutes. And so for that reason, the deaeration process and the method that's used even is effective, and it has to be proven that it's effective as well. So when I'm talking about the effects have to be determined, again, some things, there may be a slower release if media is deaerated. Now, this is commonly the effect. Remember, our gold standard is that the medium is deaerated, and if you want to not deaerate it, you have to run it that way. Usually for most disintegrating products, you're going to see not necessarily a slower result, but a more normal result. If air is present, you'll see a faster release of the drug. Again, product B, there's some that are not affected, and there are some products that may release faster, or at least appear to release faster if the media is deaerated. And these are the things that I mentioned earlier, like a basket method or even a transdermal system. Because now air is not an impediment, and it seems like the drug is releasing faster, where in actuality it's releasing as it should when air is not an influence. These issues with air, when someone goes in to sample and you have a vessel that's coated with bubbles, these most frequently cause problems with the USP qualification test. Now, there's a big, not a controversy, but there's two schools of thought on qualification. One of these rests with the performance verification test we mentioned a moment ago from USP, which is very much affected by dissolved gases, so it's critical to that process. The second, enhanced mechanical qualification, does not have a section on deaeration of media, but as recommended by that guidance from FDA in 2010, laboratories since 2010 have been required to have procedures in place to control significant sources of variability, primarily of which dissolution it could come from degassing methods. They have to be validated. They have to be, tested on, on a product-by-product basis for new drugs under development. So the second thing is laboratory purified water. Years ago, many pharmaceutical companies had an entire building or facility for producing purified water, and this was primarily through distillation. Such water was very low in dissolved gases from this distillation process. It was very often warm, temperature didn't drop too far. So it seems like a lot of methods, why aren't this deaeration mentioned in many monographs? And many older ones may not have been greatly affected by the purified water from distillation, but now things are quite different. Ion exchange beds and reverse osmosis systems are used, which operate under pressure, in some cases extreme pressure, and this saturates gases to much higher levels. Typically we may see about 8 or 9 to 10 part per million, and this can be double that when it's pressurized. So this is a big difference to understand between how testing occurred, 15 years ago and more, and how it is today. Just a little, home scribbles here to describe some of the areas of influence by dissolved gases. On the left, you'll see bubbles forming along the wall of the vessel. Again, I mentioned the turbulence at that interface, which is tremendous, and this is the area where many products are going into solution. They're heavier than water, and by centrifugal motion, they're held to the wall of the vessel as they're rotating around. So this has a huge influence. Also, the paddle dimensions cause us more shear as well. I mentioned outgassing. This is when air coming out of solution is now attaching to a particle and raising it to the surface. This can cause quite a bit of variability in test results. And then, of course, there's bubbles aggregating on the surface of a dosage form. In a way, the dose, a tablet, is a little bit of a nucleation site, and this can generate bubbles just right there from its surface. If it is a coated tablet, you may be delaying the release of that coating from dissolving. So a number of different issues. Again, product by product differences are what we need to evaluate and individual impacts of air. So at this time, I'd like to see if we, have anything in the chat box or maybe to stimulate some things popping into there. What are your observations? Have you seen issues with deaeration? And Ken, of course, you can provide your input as well, but there are a number of effects from deaeration, or lack of it, and just curious if people out in the field would like to comment on that.
All right. I'm giving folks an opportunity here to type in any questions they might have in the Q&A box. Currently, there aren't any questions, but I did want to check in with Augusta to see if maybe we've got some folks waiting on the phone line with a question.
And just as a reminder, that's *1 to ask a question with a phone. At this time, we don't have any.
All right. So
before you move on, Brian, just wanted to make a quick comment about bubbles when it comes to baskets. One of the things that I'll often see if media hasn't been properly deaerated and you're using baskets is that you'll have a large air bubble mass that will form underneath the basket, or you will have a series of small bubbles that will form on the sides of the baskets that will prevent your drug from interacting with the dissolution media as much. And that's often why you see a depressed result when it comes to a basket method. One thing to help with that beyond obviously degassing is making sure that your baskets are clean and dried very well before use. But that is something that I see pretty commonly.
Yeah, thanks, Ken, because, it's exactly right, because when they're on the sides of the basket, if you're dealing with a 40 mesh basket, you might be dealing with a 30 mesh basket if you understand in terms of openings for certain surface area. So it is restrictive, and of course then there's always that third bubble that arises sometimes trapped under the basket when this is usually when baskets are introduced wet and they haven't completely dried before starting another dose. And just from surface tension, you can sometimes trap a bubble under a basket, which is quite serious because it's about like having a steel plate under there, right, Ken? It just keeps any drug from moving around in that basket. So, yeah, those are, and typically that's not caused by deaeration, but just generally having a dirty basket or jumping on. But it's a valid point, and it's something all analysts should be looking for when they lower baskets into the vessel. Okay, so thanks for the comments there, and we're going to actually move on into deaeration procedures. We brought this topic up about 6 years ago. We were talking primarily about the effects, and I think we've revisited that in the first part, but now we're going to really look at some of these methods that people have used. And over the years, people have come up with a variety of different ways. There's been a number of papers written, and I've summarized some of the methods that have been used in the past. But these really boil down to mostly some type of method involving heat filtration or vacuum, and the USP captures that best, I think. Sometimes it's not just raising temperature or not just filtering or not just applying a vacuum, but doing a combination of some of these processes can be quite effective. The second one, helium sparging, and we're fairly used to this from de-aerating or degassing mobile phase, and this is usually something in a smaller concentration, a smaller quantity, such as a liter. You know, it's pretty easy to de-aerate a liter of material, but a dissolution analyst may go through 50 liters or more a day, not uncommon at all. So de-aerating 50 liters of media with a very effective technique, which is helium, can be a bit cost prohibitive. We'll spend a little bit more time talking about helium, but it is a good means of removing air. You're just sparging it, replacing it with a very tiny, molecule. So it is quite effective. There are also some automated methods. These are, maybe machines that use some type of gas permeable membrane. A number of these have been fairly effective, although in difficult times, sometimes getting down to the USP level of dissolved gases. And then there's a bit of a myth that you cannot de-aerate media that contains surfactants. And to tell you the truth, that's true. If it contains the surfactants, you can't de-aerate it. And really the answer to this is making the media with everything, your buffers and very close to the final volume with pH adjusted, with everything but the surfactant. And what you're going to do is de-aerate that bulk media, and then you're simply going to add a bit of that media to the surfactant, stir it for a slurry, and then quantitatively transfer that into the carboy and stir it gently. And this way you'll have perfectly de-aerated surfactant-containing medium. So there's methods that have been quite effective for removing gases, but there are some that don't work well. You'll see some graphs and charts and things of doing some of these alone, like where you sonicate under vacuum, sonicate alone, or filtration alone, or potentially using a nitrogen gas to sparge, which really forms N2 molecules, which are big enough to see and don't really, do anything. So, so some things work and some things don't work. And this is why USP, when they mention their method, they also finish that up with other validated de-aeration techniques may be used. But anyway, the USP procedure. Again, this is probably considered a bit of a gold standard. It is based on a very simple concept of boiling. The most efficient way to strip air out is literally to boil it. And by doing so, you see bubbles coming up and it's relieved. But this is totally impractical for the laboratory because of the huge energy it would take to heat up 50 liters. Boiling it is very unsafe. Imagine that much boiling water around. And then it would take so long to cool down that it's just impractical. So the method here really revolves around heating it to 41 and then filtering it under a vacuum. Now, what you can see a picture insert here of a millipore filter that I've often used for de-aerating medium. And what's occurring here is that as soon as media passes through this filter, it literally boils in the neck as it's moving down. I don't know if you can see very well with that picture, but the media itself is bubbling just as it comes through because it is stripping the air out very effectively. So with this technique and then continuing vacuum about 5 minutes, it's extremely effective at lowering dissolved gases somewhere between the 3 part per million and 5 part per million range, which is extremely effective. And again, if you want to validate a technique, it's best to do it against this technique for assurance. I started looking back through some papers. There's a couple of fantastic resources for dissolution. Obviously, the dissolution discussion group is very prominent, but the dissolution technologies publication is also quite helpful, and there's a number of articles that have appeared in here over the years. And some of these studies, this is way back in 1995, and what you're seeing is quite a few methods here that are performed individually. So remember I said that some of these individually may not do very much. I think the one big difference here is helium sparging. And with this chart, I don't know if you can see the two lowest bars, both of those are helium sparging, because if this technique is done just by itself, that probably is the most effective way. But even though some of these mention filtration or sonication or vacuum or something like that, or heating the media, done independently, it really doesn't have a huge effect on the level of air in the medium. And that's fairly obvious by some of the graphical representations that you can see there. But heating it alone, doesn't lower it very much. The idea here is to get below 50% of the O2 concentration, the saturation level. And again, that generally occurs at about 5 to 6 parts per million to reach that kind of level of O2 saturation. So we want to get it low enough because, remember, we still have to measure it and we have to get it into a dissolution vessel. So that transferring can re-aerate it somewhat. There was a paper published by Terry Moore. Terry's retired from the FDA now, but this gentleman was an authority on dissolution, and he had a very interesting procedure that the Division of Pharmaceutical Analysis at FDA had used for many, many years. And it almost seems like, how can you get rid of air by having air flow into something? But the idea here was that pressure was dropped to a point, 140 to 150 millimeters of mercury, with a controlled process using a manometer or a pressure gauge that would allow a small amount of air into it. So what seems like something just bubbling away over here is actually just keeping something mixed, but the fact when media is vacuum degassed in this way, that it was felt that this was an effective means to reduce the level of air. Now, I think in subsequent studies, it was proven that maybe this wasn't as effective as it seemed, especially relative to the USP test. It may not have been nearly as effective, but this was a standard method for removing excess dissolved gases from the media. And of course, these type of methods work much better if this media is heated. If that media is heated to 41 degrees, this keeps it from further degassing, if you're starting off with room temperature and heating up. Another publication, this particular one came from several analysts that are with Merck Pharmaceuticals. This article looked at a couple of very common techniques, obviously none being a technique. You can see some fairly high oxygen content. When nothing is done, their study started off around 13 parts per million, or 13 milligrams per liter. And through the USP test, that dropped down below 5. Some membrane degassing methods, just pulling through a vacuum through a membrane, maybe without the preheating, gets it down to about the 5.6 range or so. And then, of course, helium sparging gets that fairly low as well, down to about 5.2 part per million. So the idea here is that some of these methods are pretty good, and some, again, may not be as good. But the effect overall on the tablets, the prednisone that was used at the time, that it seemed to be quite effective for improving the results and actually providing a lower standard deviation between runs. Another publication in 2004. This was performed by a number of folks that were with Lilly up in Canada. Of all the deaeration methods that I think papers that I've read, I think this one has probably influenced me the most. There's so many things it discussed in here, not only the most efficient ways to deaerate media, but how long does it last? You know, at what point is media basically unusable or it may need to be deaerated again? So there's also some rather revealing, you know, people say that they just sparge with helium, and very often I'll ask how long they do that. They say, well, we just put a little air stone on it and just let it run for about 5 minutes, and, you know, they call that deaerated. Well, usually that has to be followed up with some type of measurement we'll discuss later, like a dissolved oxygen measurement. But for maximum efficiency, or not even maximum, but acceptable efficiency, like getting down to around the USP level, again, that's just below 3 milligram per liter, what they've found out, is that it will require a flow rate of helium about 40 milliliters a second. And they suggested over time that about 0.5 minutes per liter is effective. Now, you know, when we look at a fairly large carboy of media that we're going to go through today, if you think sparging it for 5 minutes at maybe a not adequate flow rate would be effective, it's actually not very effective at all. So you'll see here that 50 liters of medium would generally sparge for about 25 minutes, but then you've got the overall consumption of helium. That amount of helium really translates to about 60 liters of helium, which can be remarkably expensive. You know, this gas is getting nothing more but more scarce. It's a non-renewable resource as well, and it's getting more and more expensive, with some shortages experienced here and there. So a method that was used for HPLC deaeration may not have been as effective. Moving on to efficiency, the main, one of the big things that helps with the efficiency of helium sparging is using, typically what people use are the HPLC solvent inlet filters. These are generally a frit, a metallic frit that can be weighted and, you know, more or less screen or filter media before it moves into a chromatography system. But in this case, they're going to use it in quite a different manner, hooked up to a tube to a source of helium to provide a very fine dispersion of helium bubbles in the medium to sparge it more effectively. So what they pointed out in this article, especially for larger volumes now, that the 2-micron filter would be, there was definitely an advantage, especially to how long you'd have to, you know, you'd have to run this. So the bottom graph that you see there is based on, I believe, about 24 liters of media. And, you know, if you're trying to get down around to the, you know, the 3 part per million range, you can probably see that you'd have to sparge it another 10 minutes or so, as opposed to, you know, you basically double your time if you use a 10-micron inlet filter instead of a 2. So just a point there that was interesting. And on to the reaeration rate, there is, you know, things can reaerate. If you remove them, there's laws of partial pressure at work here, where air will try to reach equilibrium with the media the longer it's used, or you know, as it sits. So they compared the reaeration of media, and this was looking at, you know, several different methods. But what they pointed out was, you know, when the second bars there, that after deaeration, you're basically lowered your saturation level quite low, the amount of oxygen below or at 3 part per million. But after transfer, this will slightly rise, and especially if you've had some type of a sparging method. And we can see after temperature equilibrates, and even after about 45 minutes or so, you'll see a steady rise in that amount of gas. But I think the main thing here to remember is that it's not going to rise to a point where it's now saturated and bubbles are going to come out. In other words, it's not going to super saturate on its own. So this is quite tied to temperature. And there was another study that was done back to the folks at Merck that ran some studies back in 2004 and realized that equilibrium that I was just talking about has a natural tendency to seem to settle out around 6 part per million, around 6 milligrams per liter. They did this study by converging different media. The top 2 are basically media that has been untreated. It's not been deaerated from a couple of different sources. Placed into a vessel, it looks like it started off around 16 to 18 part per million. And it slowly, because it is degassing now, would lose air to a point where it steadies out about 6 part per million. Now, this study was done at about 5.5 hours, to give you an idea. It would take some time for it to equilibrate. But even methods that are deaerated, these will, of course, gain some air from oxygen levels from the air. But again, they won't saturate. But it's an interesting point that equilibrium, when it's reached, appears to be about 6 part per million. And I'm using that interchangeably with milligrams per liter. There was also a USP publication some years ago looking at the effects of different deaeration techniques, which lead to different oxygen concentrations in the media. And, some of these are effective and some of these are not. And I just want to explain this just a little bit. The USP procedure you see on the left, again, usually 2.8 to 3.3 or 4 around in there is typically the dissolved oxygen measurement we'd see from that. Helium sparging at room temperature is much less effective than helium sparging at elevated temperature. This has been a known fact, and heating media to 41 or 42 has been quite productive. Now, nitrogen sparging doesn't really surprise me here where it looks like it's so low. But please remember that when you sparge something with nitrogen, you're replacing air, especially oxygen, with nitrogen. So taking a dissolved oxygen measurement of nitrogen is a little bit meaningless because it's going to be very low in dissolved oxygen, but it's going to have a tremendous amount of bubbles in there from nitrogen. In other words, if there was a nitrogen sensing probe that you use, you probably see it's off the chart because it's saturated with nitrogen. So the key here is we're using oxygen as a measurement, but it has to be commensurate with the method that you're using to deaerate, if it makes sense or not to use that method. FBA technique is a total air removal process in a way, but you can see it's almost double what the USP technique is. And then there's a couple of other techniques, including, not deaerating, which is actually a deaeration technique. It sounds like I'm making fun, but it seems like to be taken quite seriously in some dissolution environments. So last slide before our next, and just to be thinking, when our next little question after this slide is going to be, what other deaeration techniques have you tried? But while you're thinking about that, I just want to mention a few things about manipulating media. And, the more you manipulate anything, the more chances are you can work air into it, especially if you've done a great job deaerating media, and then you're dumping this into the bottom of a 1-liter graduated cylinder and then pouring this maybe not so carefully into a dissolution vessel. So all that hard work you may have done to remove air may build air back into it of almost half of, at least double what was in there when you deaerated it. Some studies have also shown, this goes back to a study that was done in the late 1998 era, the 7 era, something like that. Dr. Charles Collins, he did some studies showing that about a 37% increase in the level of dissolved gases can come just from carefully measuring and transferring media. So the less steps you can do there, the better. And one of these suggestions that I think Ken and I have both used historically is weighing media. This is basically a single transfer step. You can place media directly into a vessel on a top loading balance and get very accurate weights. It's always been very helpful when you're measuring surfactants, especially because it's so accurate. But less manipulation will mean that your efficiency of your deaeration process was maintained. So also time to reaeration, typically anywhere from 30 minutes up to 2 hours, and you saw on out to about 5.5, it seems to reach equilibrium. But just remember that even though some air is partitioning back in, it doesn't mean it's going to form bubbles. Bubbles form because something is saturated and it's now coming out, or it's super saturated, and these bubbles are now forming. So anyway, hopefully that sets the tone for any discussion. Hopefully we're not going to have a real quiet group today, but it would be nice to hear from you. If you've got some other deaeration techniques, and especially if there's issues that you've had with validation, it would be great to bring those up.
Okay, thanks, Brian. Checking to see if there are any questions that are in the Q&A box here in the WebEx. I'm not seeing any, but let's just take a second and check in with Augusta to see if we've got any questions pending over the phone line.
We don't have any at this time.
Okay, thanks, Augusta.
All right, well, thank you for the follow-up. Ken, anything to add? I know you work with a lot of people on methods, and I know both of us are surprised sometimes by the methods people use and, whether or not they work. Just curious of your any additional views there.
No, I think you alluded to a couple of the major things that I see. One is there's a definite shift away from helium the last few years, given the scarcity and the variability of pricing. And I have a lot of people asking, what are some different approaches I can take, which you pointed out. The other thing which I talk to a lot of people about is determining when you might be able to not deaerate media. So we're doing a lot of focus here on deaerating properly and the impacts that those can have. But there are going to be products that don't require degassing, and you'll find that whether you degas the media or not, you'll get the same results. And so it can be really advantageous in some points to see if there might be a difference and validate that if it does look like that is the case.
Very good. Yeah, that's absolutely true. And I think it's always a crazy comment coming from me sometimes when I talk about the effectiveness of deaeration. And when you determine if a drug needs deaeration or not, let's say it doesn't need, it really should be validated against media that has been aerated. And I'll explain myself here. You want to compare aerated to non-deaerated. To deaerated. All right, compare aerated to deaeration. The reason I say you should aerate media to see if there's a difference is because the water source is so different. And I'll show a slide in a minute of these different laboratories that range anywhere from like 5 parts per million up to 18 or more, just because of the water source that they have. So even when a method moves from one site to another, you know, they may have a whole different process. Maybe one had distillation, and then, you know, the air was very low and it didn't seem to be a problem, and now it's moved to a laboratory that is under reverse osmosis, and it operates under pressure, and the level of air in the media is 3 times what it would have been normally. So anyway, it's very important to have a stable reference, and you should aerate media to really see if there's a difference between when it's de-aerated. Okay, so.
Gentlemen, we do have a question that just came in. Do you have a second?
Yeah, sure.
Okay, so the question reads, how long can you store a degassed media before it has to be degassed again?
Aha. Well, this is exactly what we're going into now, and hopefully the next couple of slides will answer that. If we feel like we haven't addressed it, we'll pop right back to it, but it is a good premonition of what we're going to talk about right now. That's the effectiveness of it and how long does it stay that way.
And in the meantime, we've received another question.
Okay, all right. Go for it.
Everybody's got a question now, which is great. I love it.
Yeah, go ahead.
So the question reads, for our PVTs, we perform in-house paddles only. My primary indicator the media is de-aerated properly is by ensuring there are no bubbles on or under the paddles and ensuring they don't redevelop. I haven't had to do the PVT for the basket apparatus, but we are planning on doing so in the future. Do you have any visual tips or tricks to ensure the media is de-aerated for the baskets?
Mm-hmm. Well, you know, what you'll see here is that we're going to talk about some measurement techniques. Now, some people have relied on the PVT itself because it is so sensitive to dissolved gases to let them know if their, let's just say, level of de-aeration is effective. I'm a little bit cautious about that for the main reason is that may be confused with something else interfering with the dissolution apparatus, like let's just say you had something vibrating on the bench which also elevates test results, you see. So it may be difficult to tease out what, you know, a positive bias is coming from. And I know this person also mentioned baskets, which can very often exhibit a lower result because you are blocking, you know, the flowability, if you will, through the basket. So let's, again, we'll look at some of these techniques, and maybe this will give a little bit better indication on some methods that we're going to suggest to be used to show acceptable de-aeration levels. And, you know, this really starts off with, you know, dissolved oxygen itself. Obviously, this is a predictable component of air, and we know by its concentration that when it is at a certain level that we have a corresponding, you know, drop in the amount of air, like total gases that would be present. Now, dissolved oxygen measurement and equipment is used all through industry. I mean, there's water, wastewater, I mentioned brewing, environmental, any type of chemical processing that may have, you know, oxidation issues, very important industrially that is monitored and removed to acceptable levels. So with dissolution, most literature is pointing to media that should be de-aerated down to at least 6 milligrams per liter or 6 parts per million to avoid bubbles. Okay, so if you start off with 6 milligrams per liter, you generally should not see bubbles form. But to me, this is right on the precipice. If it's a little over that, you might start to have interference from bubbles, but they're very difficult to see. Some bubbles are huge when media started off. It looks like, you know, you poured a carbonated beverage into a glass, and it just, you see all the bubbles on the inside of the glass. It may look like large like that, but when it's just over, it may be very tiny bubbles, very difficult to see, but it still does have an influence on dissolution. There are other meters. There's total dissolved gas meters, but these are really, they're expensive. They're really not going to give you anything over what a simple DO measurement or O2 measurement is taken from a dissolved oxygen meter. There's quite a few of these out there. There's a lot of portable ones. The technology of dissolved gas meters has gotten so much better over the years that, you know, benchtop models were usually used, and they were thousands of dollars a piece. But now there's a lot more portable handheld units that may be used. You know, the accuracy and precision may not be as great, but we're looking, you know, kind of in the accuracy in the 1/10 of a part per million range would be helpful. And many of these may be. Of course, these membranes do have to be replaced, and there is a fluid that goes in some of these membranes as well. So it's a bit like maintaining it. We don't want the membrane to rupture or anything. So they do need a little bit of upkeep. But to the point of we made earlier about the different sources, you know, the person that wrote in about, you know, best way to tell, you know, the effectiveness of deaeration. And like anything, it's like what you start with that is of the greatest concern. And, you know, I can look at this chart and almost tell laboratories, probably like A, B, C, and perhaps J, that may have been producing water many years ago. This article came out a while back, but may have been produced from distillation, which was not an uncommon practice, you know, 15, 20 years ago. Some of these larger ones, the laboratory G, H, and I, most assuredly are coming from some type of ion exchange or reverse osmosis system where pressurized water is used. So understand what you're dealing with, and throughout the day, of course, these levels can change as well. It may start off very high and then drop during the day, or vice versa, depending on when the plant is generating the most water at high demand periods. So anyway, the key thing is to evaluate water on a saturated basis, and then once you've deaerated it sufficiently down into the, you know, below generally 5 part per million or so, that should be very minimal impact. So for anybody wanting to monitor it, again, I'm going to strongly suggest a dissolved oxygen type of measurement. And again, this goes in with a recommendation directly from the dissolution chapter, which is harmonized with the European and the Japanese pharmacopoeia, that, you know, where dissolved gases, you know, they can cause bubbles to form, which change the results of the test. If dissolved gases influence the dissolution results, dissolved gases should be removed prior to testing. You know, very interestingly, there's only a handful of monographs that say anything about deaeration. Now, why is that? Well, that's because of the statement that's in 711. That's the one that verifies that you've challenged that method, and if it is affected by dissolved gases, it's removed. Okay? I further want to mention that USP monographs, as well as the methods in the FDA database and methods in the USP database, the erroneous part of that description is the word method. Those are not methods. Those are run conditions. Monographs and all of the databases just show you the apparatus, typically 1 or 2. It'll show you the media, the volume, the time points that are pulled, and also the, for instance, the acceptance criteria for that, and of course the speed of the apparatus running. So there's about 6 things, and it just lists as run conditions. But what those monographs or things don't tell us are the effects of deaeration. Just like we don't know if sinkers are needed, or what type of filter to use, or how much to waste through a filter, or what are the stability of our analytical solutions. Are these light sensitive or sensitive to something else? So, you know, these are things that have to be challenged in a method that is developed from a monograph. That's why I'll say challenged when developing and validating a method obtained from the monograph, because technically we don't have a method, we just have run conditions. And dissolved gases is prominent the main thing that has to be evaluated along with filters and so forth. Other recommendations is to use an effective and validated technique. The USP procedure, again, being a standard, I showed you a method in a slide back there that allowed one vessel to be heated to 41, and then you're pulling the media through a filter by applying a vacuum on a second jar. This is very effective, and when you dissolve gases, really should not have an impact on results if it's been properly deaerated. But if you can keep it at around 5, and then it generally does not get above 6, as we showed in that graph, this should be sufficient on controlling the amount of air that will exist within the dissolution test. So real samples with or without deaeration, monitor O2 levels. You should make observations like one of our guests suggested, but I would suggest that a measurement be taken for most assurance, and then validate that method so it's written into a procedure, and now all of your analysts will run that the same way. So differences really shouldn't be greater than 3%. If you're running 2 products, for instance, let's say you are using a PBT as a final check, you shouldn't see the difference at each time point, or especially a PBT at 30 minutes, of greater than about 3%, would be my suggestion. Other things I think we've already mentioned, the purification through RO and ion exchange, pressurized. Many older methods were developed under distilled water conditions, which were very low. So this may, again, cause some confusion over, whether deaeration is required or not. But it is on a side-by-side comparison during development that has to be performed. Just a few concluding notes, and then we'll open it back up for discussion. Helium sparging is very effective. It can be extremely expensive. It is non-renewable, as Ken had mentioned, and we basically derive what we have from mining of natural gas. It's a byproduct, but very difficult to extract and also to preserve. So poorly soluble drugs also show quite a difference between non-deaerated and deaerated medium. But most immediate release dosage forms, this is so important, are affected by bubbles. And the idea here is because immediate release products for quality control have a single limit, Q, which is a single lower limit. There's no upper limit. So what we run the risk is if we have a batch that is subperforming, it should not be released. If we test it incorrectly without properly challenging deaeration, we could result in a product that is released into the field, which could cause health issues. Our job as analysts is, I often say, is not to get product out the door. It's more to catch the products that should not get out the door. It should not be released to public. So it's our responsibility not to help a drug pass. The idea is to be able to police it and ensure that we are retaining the ones that do not meet specifications. So this only comes about with, by removing that interference that dissolved gases provide. So anyway, I want to suggest that, the length of time that the person suggested, hey, how long does it last before it's good? Typically, I think some of the studies, the paper that I mentioned from Lilly, and that's found in Dissolution Technologies, that paper was extremely good as far as describing, the methods and how long that they lasted. That article came out in 2004. So if you'd like to search that in Dissolution Technology, it was a comparison of the effectiveness of various deaeration techniques. And they go into some discussion there about how long it lasts. And it seems like it was about a day to a day and a half, depending on the level that was reached. You know, getting it down below about 2.8 part per million. So anyway, I'd like to see if there's other questions or comments. I really look forward to your comments, like your view on some of these things. You know, what other measurements have you performed or used? And I'd be very interested to hear. And Ken, of course, if I've left something out or misrepresented anything, please, or you can add to it, please do so.
All right, guys, we do have a couple of questions pending. First one reads, do you have any recommendations for preventing air bubble introduction when using a dialysis cell or suspension cup during dissolution?
Now, the suspension cup was mentioned. This is a thing that basically holds a type of very viscous suspension. These may be like an intramuscular IM injection. Some are used for human use, some for veterinary, but it may be more of a depot injection. When these are placed in there, very often we trap a bubble in there, just either by shaking a sample or putting something in there. And I remember some of those methods that we used to test that we had a final criteria like any suspension of a weight. In other words, you know, you're not calculating dissolve, you know, percent dissolved by weight. You are, however, weighing how much drug you put into a cup or into a vessel by difference. So if you're using a syringe, you can tear it, you can put your drug in it, weigh it again, expel your drug into either a vessel or the suspension cup, and reweigh that syringe again. Now, the weight difference here is only telling you that you got the proper dose in there. And that, of course, depends on the specific density of your drug. You would have to take in either a pycnometer or some other means of determining the density of the drug without air bubbles. But usually to remove those, and again, the idea of the weight is just to show that you got the proper dose in there. So each dose is relative to a certain weight. You can determine that and write that weight into a dissolution method, very helpful. Now when somebody introduces it, they can refer directly to that weight and ensure that they are in the right range of that required for the dose. Very quickly though, if there are bubbles in your sample, they very often can just be tapped on a countertop. Most suspensions you need to let settle for about 5 minutes anyway to show that you know, air has been allowed to rise to the surface, and you generally sample from the middle of the container. So that'll hold down on bubbles to start with.
All right, thank you. Next question reads, and this could be lengthy, so we have noticed a shift in the dissolution profile during our method transfer to an overseas lab. What could be the root cause?
Wow, that would be a good topic for a future discussion, right, Ken? Method transfers. I know we've had one of our previous episodes, I can't remember how long ago it was about method transfers, you know, the variability that can occur. Certainly purified water sources could change, but also, you know, just laboratory conditions, reagents that are used. There's so many things that can affect the transfer of one method to another. You may see a higher bias in results or a lower bias, and very often this can be tracked to materials, like even down to the filters that are being used, syringes, compatible components, is automation being used, but deaeration is one of those things that's forefront. Are they using the same method to deaerate, or are they using deaeration more like a verb, like, you know, I'm deaerating something, but without regard to how effective it is? So I think that using some of the techniques and things we've discussed today to be able to actually measure the dissolved gases is very important. But also after you have, like, either weighed out or, volumetrically measured your media, now you poured it into a vessel, is to take those measurements again, just to see if you've come above that, 6 part per million level. That could indicate that now you've got a super saturated situation, and bubbles may form at 37. So 37 degrees. So all of these are quite critical. And of course, one thing we do want to eliminate is the influence of deaeration. So it should be way at the top of the list on things to check for a method transfer. That was a very good question.
All right, perfect. I'm not seeing any other questions coming in through, oh, yes, that would be a line. Here we go. That's it. So my question is, what should be the procedure to evaluate such equivalence? How much data needs to be generated for equivalence? So that's in relation to the question, I guess, you've just been discussing.
Yeah, it's interesting. Most equivalents we show usually as replicates of 3 minimum. If you're going to be looking at batches of air, I would, of course, take something as simple as water, but you're also going to want to demonstrate effectiveness in various media, possibly, if they're using a lot of phosphate buffer, things like that. I would stick to verifying it with dissolved oxygen, personally. If you do that and you have a technique that is effective, that should be reproducible. Some of the hints were given for sparging, like how long that's done. Of course, anytime that you don't sparge it as long or you use a lower flow rate, you're subject to not having a procedure that's as effective. So it's very important to develop a procedure. We've given you some ideas, so some things that we would prefer and some things that, perhaps if you can afford it, maybe helium would be a good choice. But again, it's supply and environmental-wise, it might not be a great choice, especially the cost. But anyway, it's important to basically to validate that shows that it's equivalent to the USP method. So set yourself up to do a USP method and understand those levels according to, readings you're getting from a dissolved oxygen meter. And if you propose a different technique, I'm okay with that as long as it's not markedly different in terms of dissolved gases from another method. We've shown some various slides. Remember, this will be a recording, so you can refer back to it if you have a question about some of the slides or content. But anyway, I hope that helps. Ken, anything to add there?
If they're referring to showing equivalence between results of not degassing and degassing, that's often done through an F2 comparison. Usually there you would take 2 dissolution runs with the USP degassing approach and compare that to 2 dissolution runs without degassing or with whatever alternate technique that you have. And so that can show with that given formulation that you don't have an impact. So I often see that used as a standard as well. But if you are using an alternative degassing approach like Brian said, looking at a total dissolved gas meter would definitely give you the option for those as well to see what that result is directly.
Yeah, just to reinforce what Ken said, it's important to aerate media and compare that to deaerated, not just take your water source because it may be barely above or way above an oxygen. We just don't know. So it's important because we don't know even how much water fluctuates in the laboratory. It'd be very interesting to take DO measurements over a day to find out how reproducible your oxygen levels are. There may be some of that available in the standard water testing that a lot of laboratories do, but it'd be very interesting to chart that to get an idea if it's something controllable.
All right. Let's begin with Augusta and see if we might have anybody pending over the phone line.
Sure.
We don't have anyone at this time.
Okay. Thanks so much, Augusta. Brian, did you have any closing remarks?
No, other than apologies for running over again. This is it's fun having a discussion group, and we've had some good input today. So anyway, I hope this was helpful. You know, hopefully you can meet up with us next time. I did put a list of those papers that I referenced for some of the work here, so you can go back at your leisure and look at some of those topics. Just a reminder, our next topic is coming up August 8th. This will also be very interesting on sink conditions, and a very often asked question about surfactant level justification. How do you justify levels of surfactants? So we hope you can tune in for that, and we look forward to seeing you next time. We're seeing you throughout just continual discussion on the discussion group on the bulletin board. So my thanks for attending, and to Ken, Sandy for pulling all this together, and we look forward to talking to you next time. Thank you, and have a nice day.
All right. Well, thank you both to Brian and Ken for a wonderfully informative presentation and discussion. Just a note in closing then to our attendees. So following this event in approximately 24 hours, you will receive an email that will contain a link to the recording of this presentation. So you'll know how to go back and reassess some of those sections that you want to bone up on, if you would. It does appear that we have no further questions, so I would like to close the webinar at this time. So thanks again, Brian and Ken. And on behalf of the Dissolution Discussion Group, we thank everyone for joining us today, and we hope to see you at a future DDG online meeting. So have a great day.